We are going to define what it means to call something the lim sup or the lim inf of a sequence. Lim sup is actually short for limit superior, whereas lim inf is actually short for limit inferior. Okay, so let me just begin by defining lim sup and lim inf. I will start with lim sup. Okay, so consider a sequence xn. Okay, we're going to consider two cases in the definition of lim sup. If the sequence is unbounded from above, then by definition we say that the lim sup of the sequence, which is denoted by lim sup xn, is equal to infinity. Okay, so if a sequence is unbounded from above, we just define its lim sup to be infinity. If not, in other words, if xn is not unbounded from above, is bounded from above, we define the lim sup as follows. Lim sup xn is equal to limit as n goes to infinity sup Okay, so let's stare at this a bit. If xn is indeed bounded from above, then the lim sup is defined as the limit as n goes to infinity of a certain sequence, right? This sequence, let us call it Vn. What is this Vn? Vn is the supremum of the values taken by the sequence to the right of position n. In other words, it's the supremum of a set composed of all elements xk where k is greater than n. So Vn is once again the supremum of the values taken by the sequence to the right of n. Okay, now because the sequence is bounded from above, the supremum is being taken corresponding to a set that is also bounded from above. Right? So because of the fact that my sequence is bounded from above, Vn is in fact a real number because the set whose supremum Vn is defined to be is also bounded from above. Right? So in this particular case, note that, so that's the end of the definition. Now I'm going to interpret the definition. Note that in the latter case, firstly, Vn belongs to R, right? Because if you take the supremum of any set that is bounded from above, that is in fact going to be real valued. This follows from the least upper bound property of the reals, right? Additionally, you can also see that Vn is a decreasing sequence. Why? Because as n becomes larger, you are basically taking supremum of a smaller set. Right, so consequently Vn is a decreasing sequence. Make sure that you convince yourself of this. So if Vn is a decreasing sequence of real numbers, that means that limit n goes to infinity of Vn exists. This implies that lim sup of xn, which by definition is the limit as n goes to infinity, Vn exists. And moreover, it exists in either R or it takes the value minus infinity. Right? So if you patch both of these things together, what you see is that if a sequence is unbounded from above, by definition we say that its lim sup is plus infinity. If it is bounded from above, we define the lim sup as the limit of Vn, which is the supremum of the values taken by the sequence to the right of n. in this latter case, Vn is real valued and Vn is a decreasing sequence. Any decreasing sequence will have a limit, either real valued or minus infinity. When will it have a real valued limit? If this decreasing sequence also happened to be bounded from below. If it is not bounded from below, then the limit would be minus infinity. Right? So if you patch both of these together, you lead to the conclusion that the limb soup exists for all sequences. Right? All sequences need not have a limit, as we have clearly seen. However, the limb soup is actually well defined for all sequences, and the limb soup can be any value in the extended reals. Limb soup can be plus infinity in the case of a sequence that's unbounded from above, or the limb soup can be a real number or minus infinity, in which would happen if the sequence is in fact bounded from above. Okay, so that essentially is the formal definition of the limb soup. So now I'm going to give you the parallel definition of the lim inf. Once again, consider a sequence xn. Okay, if xn is bounded as unbounded from below, by definition, I'm going to say that the lim, write that again, lim inf of xn is equal to minus infinity. Okay. On the other hand, if it is bounded from below, then we will say that lim inf is essentially the limit as n goes to infinity of the following sequence. Infimum of the values taken by the sequence to the right of n. Okay, so that's the definition of the lim inf. If your sequence is unbounded from below, I'm going to define the lim inf to be minus infinity. If it is bounded from below, then the lim inf is in fact the limit of the infimum of the tail values of the sequence, the values of the sequence taken to the right of n. Now, because my sequence is bounded from below, this set of values taken by the sequence to the right of n is also bounded from below, and so this inf is in fact well defined. Right? So let's call this un now. This un is in fact real valued in the latter case. So in the latter case, clearly this un belongs to R, and moreover un is an increasing sequence. Right? So which implies that the limit of un, which is by definition the lim inf, exists in R or plus infinity. Right? In this un is an increasing sequence of real numbers. If that sequence were unbounded from above, then its limit would be infinity. If it is bounded from above, the limit would be real valued. Right? So this is how you define the lim soup, the lim inf of a sequence. And once again, from this, you can see that the lim inf is defined also for any sequence. Right? So what we have done so far is basically defined formally what is the lim soup of a sequence, what is the lim inf of a sequence, and importantly, while every sequence need not have a limit, every sequence is guaranteed to have both a lim soup as well as a lim inf. Alright, so that is the definition of lim soup and lim inf. A straightforward consequence of this definition, which I'm also going to leave as an exercise. This is actually these are all 2-line exercises. The thing to note is that for any sequence, the lim sup is in fact always greater than or equal to the lim inf. Right? And again, this is not difficult to prove at all. You just have to look at all the different cases. So to me, this is primarily an exercise in you internalizing the definition itself. Right? So first consider the case that your sequence is unbounded from above. If it's unbounded from above, then the lim sup is plus infinity, so there's nothing left to prove. If the sequence is unbounded from below, then the lim inf is minus infinity, in which case again there's nothing to prove. If the sequence is bounded on both sides, right, then we know that the lim sup and the lim inf are both in fact real valued. In that case, you have to show that the real valued lim sup is in fact greater than or equal to the real valued lim inf. Okay, so that is something I'm going to leave as an exercise to you. What I'm going to do is basically prove our main result for this video, which is the following. Let xn be a sequence. There are two parts to this theorem. The first part is that if the limit exists, again, when I say limit exists, I'm not saying that the sequence converges. The limit exists means that the limit could be anything in the extended reals, right? In that case, the lim sup and the lim inf agree with the value of the limit. Then lim sup xn is equal to lim inf xn is equal to limit n goes to infinity xn. The second part of the result is a kind of a converse. If the lim sup and the lim inf agree, then in fact the limit also exists and matches this value. Okay, so if you patch this together with the above lemma, the lemma that's been put above the theorem, then you get a clearer picture of what lim sup and lim inf is. Once again, I emphasize that lim sup and lim inf are in fact well defined for every sequence, irrespective of whether the limit exists or not. In general, the lim sup is always going to exceed the lim inf. The lim sup will always be greater than or equal to the lim inf. What the theorem tells you, by considering both case 1 and case 2, is that the limit of a sequence exists if and only if the lim sup and the lim inf agree. Right? And there are two parts to this, of course. If the limit exists, then we show in part 1 that the lim sup and the lim inf agree and take the same value as the limit. Conversely, if the lim sup and the lim inf are equal, then the limit also exists and matches the same value. Okay, so the overall takeaway of this theorem is that limit of a sequence exists if and only if lim sup and lim inf agree, right? And for cases where the lim sup is strictly greater than the lim inf, those are precisely the sequences for which the limit does not exist. Okay, so this is basically a takeaway from the theorem statement itself. Okay, so now I'm going to actually go about the proof of this statement. So the proof, as you can see, is in two parts. So part 1. Right? So for part 1, we know that limit exists. Limit n tends to infinity, xn exists. Okay. So now I'll actually have to take three cases, three sub cases, right? One where this limit is in fact plus infinity, the other where it is minus infinity, and finally the case where it is real valued. Right? So let's say case A is where limit of xn is in fact infinity. Right? In this case, if the limit of a sequence is infinity, then it is trivial that the sequence must be unbounded from above. Right? So it's easy to see that in fact that would imply that the lim sup of xn is also equal to infinity. Right? Because the sequence is unbounded from above, which means by definition that the lim sup is infinity. So the only thing left to show is that the lim inf is in fact also infinity, which is also a straightforward consequence of what it means for xn to tend to infinity. Okay, so given some, let's say, threshold m which is greater than 0, by definition there exists some n naught such that xn is going to be greater than m for all n greater than equal to n naught. This is what it means to say that xn tends to plus infinity. Okay, but since for all n greater than or equal to n naught, xn is greater than m, the infimum of the tail values of the sequence must also necessarily be greater than or equal to m. This means that the infimum of the values taken by the sequence, let's say to the right of n, this is exactly what we called un in the definition, if you recall. This is in fact also greater than or equal to m for all n greater than or equal to n naught. Okay, so that is kind of all there is, right? For every m greater than 0, there exists an n naught such that un is greater than or equal to m, which implies that un tends to infinity, which is exactly what I want to prove. Okay, so that's really all there is to show, that if the limit is infinity, then the lim sup and the lim inf must necessarily be infinity. Now, the part B where the limit is minus infinity also follows along similar lines. So I don't need to sketch that argument out. I will have you check that it holds. Similar arguments apply. Right? So similar arguments can be used to argue that if the limit of the sequence is minus infinity, then the lim sup and the lim inf will in fact both be minus infinity. Okay, so now let's come to the interesting part of the theorem, the interesting third case where the limit is in fact real valued. Okay, so the limit is real valued. Let's call the limit x. Okay, now by definition, what does this mean? This means that given epsilon greater than 0, any epsilon greater than 0, there exists an n naught such that in absolute value xn minus x is less than epsilon for all n greater than or equal to n naught. Right? In other words, xn is sandwiched between x plus epsilon. In fact, these inequalities are strict, so I can just write greater than, which is greater than x minus epsilon for all n greater than or equal to n naught. Right? An immediate consequence of this is that if I look at the supremum of the tail values of the sequence, in other words, if I look at Vn, what is Vn? It is the supremum of all values taken by the sequence to the right of n. Since every value of the sequence is upper bounded by x plus epsilon to the right of n naught, it follows that Vn is in fact going to be less than or equal to x plus epsilon for all n greater than or equal to n naught. Similarly, since un is the infimum of all the values taken to the right of n, this is also going to be greater than or equal to x minus epsilon for all n greater than or equal to n naught. Because for all n greater than or equal to n naught, the values of the sequence themselves are sandwiched between x plus epsilon and x minus epsilon. So any sup of a subset of those values or any inf of a subset of those values will also be suitably sandwiched. The sup, which is these Vn's, are necessarily bounded above by x plus epsilon, and the infs, which are denoted by the UNs, are necessarily bounded below by x minus epsilon. Okay. Now Vn, remember, is a decreasing sequence, and for all n greater than equal to n naught, Vn is in fact less than equal to x plus epsilon. So which means clearly the limit as n goes to infinity must also be less than equal to x plus epsilon. So I conclude that lim sup of xn, which is just the limit of the Vn's, is going to be less than equal to x plus epsilon. Similarly, from that condition on un, I conclude that the lim inf of xn is greater than or equal to x minus epsilon. Remember, un is an increasing sequence, and beyond n naught, the values taken by the sequence un are greater than or equal to x minus epsilon. So the limit must also obviously be greater than equal to x minus epsilon. So in particular, both of these properties are true for all epsilon greater than 0. Okay, what does that mean? What that means is that the lim sup of the sequence is less than equal to x plus epsilon for every positive epsilon. Similarly, that the lim inf is greater than or equal to x minus epsilon for every positive epsilon. Since this is true for every positive epsilon, I can now conclude that the lim sup of xn is actually less than equal to x, right? And moreover, the lim inf is greater than or equal to x. Yeah, so the first part of this inequality comes from this part comes from the condition that the lim sup is less than equal to x plus epsilon, and so this is true for every positive epsilon, so the lim sup must be less than equal to x. The second part of the inequality I've written comes from here, which is that the lim inf is greater than or equal to x minus epsilon for every positive epsilon, so therefore the lim inf must also be greater than or equal to x. If you patch both of these together, remember, we already know that the lim sup has to be greater than or equal to the lim inf. We know that the lim sup of any sequence is greater than or equal to the lim inf, right? So if you now combine both of these statements, on one hand lim sup is greater than equal to lim inf, on the other hand you have said that lim sup is less than equal to lim inf. In fact, lim sup less than equal to x less than equal to lim inf. Both of these statements could only possibly be true if the lim sup and the lim inf are both x. And that completes the proof. Right? So if you patch all of this together, what you will conclude is that we have shown the first part of the theorem, which is that if the limit exists, then the lim sup and the lim inf will agree and match the value of the limit. Okay, so that side of the theorem is now proved. Now we have to go on to part 2 of the statement. Now remember, the hypothesis for part 2 is that the lim sup and the lim inf agree. Okay, in this case we have to show that in fact the limit exists and in fact matches this value. Okay, so again, as you can imagine, there are going to be 3 subcases here. One subcase where the lim sup and the lim inf are both equal to plus infinity, the second where the lim sup and the lim inf are both minus infinity, and finally the case where the lim sup and the lim inf are both real value. Okay, so the first 2 cases are in fact trivial. If lim sup xn equals lim inf xn is equal to plus infinity, what you have to show is that then in that case the limit is also equal to plus infinity. This is easy and left as an exercise, right? So in this particular case, when you go through this, you will realize that the lim sup is infinity is irrelevant. The fact that the lim inf is infinity itself implies that the limit of the sequence is equal to infinity. Okay. Similarly, the case where the lim sup and the lim inf are both minus infinity is also straightforward. Again, in this case, you will see that the lim sup, the lim inf being minus infinity is irrelevant. After all, if the lim sup is minus infinity, you are guaranteed that the lim inf is minus infinity, right? Because you know that lim sup is greater than or equal to lim inf. So here what you have to really use is the fact that the lim sup is minus infinity implies that the limit is minus infinity. Also an easy exercise. Okay, so now all that remains is perhaps the interesting case of the proof, which is part C, is that the lim sup and the lim inf are both real valued. Is equal to x in R. Alright, so now I have to prove that the limit also exists. Okay. So this is also going to be straightforward. So given epsilon greater than 0, the fact that the lim sup is equal to x implies the following. There exists, let's say, an n1 such that the supremum of xk, where k is greater than n, is in fact less than, so this is Vn, remember, right? This is less than x plus epsilon for all n greater than or equal to n naught. Okay, so what you can conclude from here is that for all n greater than or equal to n naught, this Vn is in fact going to be less than x plus epsilon. Now this Vn is after all a supremum. It's a supremum of the values taken by the sequence to the right of, well, n. So therefore the fact that this is true for all n greater than or equal to n naught in fact implies that the values of the sequence themselves are also upper bounded by x plus epsilon for all n greater than n naught. Right? In particular, the fact that the earlier result that Vn is less than x plus epsilon holds for n greater than or equal to n naught means that it holds for n naught, right? Which means all values of the sequence taken to the right of n naught, which means for all n greater than n naught, that the supremum of those values is less than x plus epsilon. If the supremum is less than x plus epsilon, then clearly every value is also less than x plus epsilon, which is really all that I have written. Okay, so xn is therefore greater than x plus epsilon for all n greater than n naught. Similarly, for the same epsilon greater than 0, or given any, similarly there exists some n2 such that the infimum is greater than x minus epsilon. This object is what we called un. Okay, so the fact that un converges to x implies that for the same epsilon that I have chosen before, there exists some n2 such that un is going to be greater than x minus epsilon for all n greater than or equal to n2. Oh, I've made some mistakes here, right? So instead of n0, let me use n1 here. I've been using n1 so far. Similarly here I'm going to call it n2. Yeah, sorry about that. You should be able to go back and convince yourself that what I've been calling n0 temporarily here actually should have been n1, because remember n1 is what I used here. Okay, so again, so this un is going to be greater than x minus epsilon for all n greater than equal to n2. An immediate consequence of that is that every tail value of the sequence is also greater than x minus epsilon for all n greater than n2. Why is that? Just apply this fact that un is greater than x minus epsilon at n is equal to n2. If you do this, you will see that the set of values taken to the right of n2, the infimum of that is greater than x minus epsilon. So clearly every value of the sequence is greater than or equal to the infimum, which in turn is greater than x minus epsilon, right? So that's what I have written here. Now now we are back to the old trick where I have this statement 1 here and this statement 2 here. Both of these together imply the final result I want. For this I'm of course going to define let n0 be the max of, let's say, n1 and n2. Right? So to the right of n0, in fact, both of these properties must be true, which implies that absolute value of xn minus x is less than epsilon for all n greater than n naught. Right, now in the definition I have used greater than equal to n naught, but all of this is really irrelevant, right? If this is true for all n greater than n naught, it is true for all n greater than or equal to n naught plus 1. So it doesn't really matter whether you use a greater than symbol here or greater than or equal to. Okay, so for any given epsilon greater than 0, we have shown that the values of the sequence are within epsilon of x for all n greater than n naught. So such an n naught always exists. That in turn obviously implies that the limit as n goes to infinity of xn is equal to x. In other words, the limit matches the lim sup and the lim inf. So to reiterate, what we have done in this video is defined the lim sup and the lim inf. So there are two morals here. Right? And the first is that lim sup and lim inf always exist. Right? And the second is that the limit of the sequence exists if and only if the lim sup is equal to lim inf. In which case the limit will in fact match the value of the lim sup and lim inf. In general, yeah, maybe there's a third moral after all. In general, the lim sup will be greater than or equal to the lim inf. Yeah, so I should have probably ordered them as 1, 3, 2. Lim sup and the lim inf always exists. In general, lim sup is always greater than or equal to lim inf. And the limit of the sequence exists if and only if the lim sup matches the lim inf. Okay, so that brings us to the end of this topic. In the next, we are going to talk about Cauchy sequences.